revise what we discussed in the previous lecture, and then I will start some more examples. So basically we are discussing when a linear map from a non-linear space to non-linear space, when it becomes continuous. So these are the equivalent conditions which we already know, and particularly we are going to use this alpha condition that is known as the boundedness of a linear map. So to check the continuity of a function, we will always check, we will mostly check the whether that to check it is continuous, we will check the boundedness whenever the function is linear function. And one more equivalent condition which we discussed in the last lecture, that is in terms of quotient spaces. So F is a linear map from non-linear space X to non-linear space Y. That function is continuous if and only if the kernel is closed. So kernel set of all elements in the kernel, that set is closed, and the quotient map F tilde is also continuous. So this is one of the equivalent condition, and then we discuss an example of a discontinuous function, which is a linear map defined on infinite dimensional vector space. So we know that C101 is an infinite dimensional vector space, right? Because in C101 there are infinitely many functions which are linearly independent. So those functions are, if we talk about the function in variable t, then the functions are 1 t, t square, t power n, and so on. So those functions are one-time differentiable function, and they are continuous on closed interval 0, 1, differentiable one time on open interval 0, 1. So X is an infinite dimensional vector space because it has a subset which is infinitely many, a set which is linearly independent, which has infinitely many elements, and with respect to the supremum norm. So in particular, the set of all polynomials is a subset of this set, and that is also infinite dimensional. So C101 is infinite dimensional, and then we discuss a linear function which is the differential operator. So capital F maps x to derivative of x. So here derivative of x we are taking with respect to t. So that is dx by dt. Because x we are considering as a function of t. So if you take the sequence of elements of the domain, that is t power n, and each of these elements has norm 1 in the domain, but it doesn't satisfy this condition for any alpha, because if there exists alpha, then image of xn fxn in the sup norm is exactly n, and that will give us n is less than equals to that fixed number alpha, which is a contradiction because n is varies over set of all numbers, set of all natural numbers, so that is a contradiction. So this is the first example which we discussed in the last lecture, which is a discontinuous function on the infinite dimensional vector space. I think one more example we discussed earlier in terms of en by n. That was another example, but there we did not use this alpha condition. Here we are using alpha condition. So what is the speciality of this example is, here we are taking the differential operator. So what will be the kernel of this function? Capital F is a linear transformation. So what will be the kernel of capital F? So kernel means basically we need to find all x such that its derivative is 0.
Constant function. Constant.
Right. So that is a kernel. Let us write down that. Moreover, So first of all, let us talk about the range of the function. So range of the function, y is a function in the range if and only if there exists x in C101 such that f of x is y. Right. So this is meaning of y is element of the range, and we know that f of x is x dash, so that means x dash is y. Right. So is it true that this function is onto function? So what is the range? Range is basically subset of codomain. Codomain is continuous function on closed interval 0 to 1. So if we have a function y in closed interval 0, 1, then can we find a function x that its derivative is y? If we are given a continuous function in C01, can we find x that derivative of x is y? So then what is x? So for example, if we are given t square, so that is derivative of x. Then what is x?
T cube by 3 here.
Yeah, so that is basically antiderivative integration, right? So we know the fundamental theorem of calculus. So given any y in the closed interval 0 to 1, we can define the proper integral. So x is a function from closed interval 0 to k, such that xt is equals to integral 0 to t ys ds. Right, so we are defining x function in this form, and then what is the derivative of x with respect to t? You recall the first fundamental theorem, then derivative of x with respect to t is y at this point, right? Y evaluated at this point. So yeah, so therefore dx by dt is equals to yt. So this is a function of t. Basically, this means in the other notation, this is x dash is y. Right. So that is what we were looking. So if y is given, what is x? So that x dash is y. So x is this function. Okay, so that means what we have just proved is basically we proved that this function capital F is always onto function, right? So therefore F is onto function. It is already linear map. It is onto map, and the last condition is what is the kernel. So as we have discussed earlier, the kernel of F is basically the set of function x that fx is 0, and that is basically, yeah, so x where x is in C101 in the domain, first derivative, and fx is 0. Fx is 0 means derivative is 0. So what are the function which are continuous and one times differentiable whose derivative is 0? So answer is the set of all constant functions. basically we are taking the function whose domain is close interval 0 1. So all constant functions defined on close interval 0 1. So that is the kernel of this map, the differential operator. The kernel is set of all functions which are constant. So this is basically we are using uh, mean value theorem here to recall the proof from calculus. Okay. Now, if you recall, we discussed some definition of functionals. So can you recall what is the definition of functional? We define functionals when we discuss some results of linear algebra. Functionals are basically the linear maps whose codomain is one dimensional. So let X be a vector space and f from x to k. So k is either set of real number or complex number. F be a linear function. Then f is called a functional. Basically, it is linear, so it is a linear functional. And the question is whether such functional, what are the examples of the functionals which are continuous? So usually, if you recall from linear algebra, functionals are important to study the dual species. So dual species means the set of all homomorphisms from X to the set of real numbers. So we, to study the dual spaces, we need functionals. So let us see some examples of functionals which are continuous as well as discontinuous. So let us define the function again on the same space. So let f from p101 to k defined by f of x we are defining to be first. So this we already defined, right, in the previous function. So yeah, so we are using actually small f or capital F, doesn't matter, right? In this example, we were using capital F notation, but here we are using small f. So this function f is what we use in the last example, but now we want scalar. X dash is a function. To get a scalar, what we will do is we will evaluate this function at the end point. So x dash evaluated at 1. Right. So what is the function? Function is whatever one-time differentiable function is given, we will differentiate it one time and evaluate it at t is equals to 1. So question is whether this function is linear. So can you check it? So obviously we need to check it preserves addition and scalar multiplication. So clearly f is linear. because if you take fx plus y, x and y are two continuous functions, then by definition it is x plus y, its derivative evaluated at 1. And then we know that from the derivative rule, this is x dash, x plus y dash is x dash plus y dash evaluated at 1. And then we know the addition defined in this vector space, that is pointwise. So this is x dash evaluated at 1 plus y dash evaluated at 1. And then what is this? This is nothing but fx plus fy by the definition of the function. So similarly, it preserves scalar multiplication. Right. So yeah. So that is the thing. So now the question is that what is the next question? You check it is linear. Now what?
That is scalar multiplication property.
No. So we are discussing basically continuity. So in this example, we check the function is linear. Now scalar multiplication is easy. You can verify similarly the other property of the derivative. Alpha times x dash is alpha x dash. So only that thing we need to use. So now next question is whether this function is continuous. So for continuity, what we require on the vector space? So for continuity, we need a topology or basically the convergence. And convergence, we need norm on the topological space, domain and codomain. So codomain is a real number or complex number. So we have already the norm is modulus, but here we need norm. So norm we have earlier discussed in this example that on C101 we will define the norm of that is supremum norm, right? So the same norm we'll use here. So now consider we can't discuss continuity on a vector space. We need non-linear space. So now consider supremum norm on C101 and the modulus on K. So now on domain and codomain we have norm. So now we can discuss the continuity of this function, that whether this function is continuous or not. And then again to check the continuity, either we check the definition that xn converges to x implies fxn converges to fx. That also we can try to do here, but what we will do is we will use this criteria. So what we will show is that whether we are getting such alpha or not. So mostly if you recall what we have done in this example, in the previous example is, what we have done is we have constructed a sequence of elements of norm 1 in the domain, and then we have shown that its image is basically unbounded, right? So alpha doesn't exist. So that is exactly this condition. So similarly in C101 again we will try to define. We will consider a sequence of elements which is norm 1, and we will show that when we apply the function, that set is unbounded. So again, what sequence we have taken in this example, let us try the same sequence, t power n. So note that for xn t, so these are elements of domain C101, that is t power n, t belongs to closed interval 0, 1. So for this set, all of these elements has sup norm 1, right? But when we apply the function f of xn, what is f of xn now? F of xn is derivative of xn evaluated at 1. What is the derivative of xn evaluated at 1? What is that value? Xn is t power n. So its derivative is n into t power n minus 1. So when we evaluate it at t is equals to 1, we get the value n. Right, so fxn is n, and then if we find its norm in the codomain, fxn is the element of codomain, right? Because we applied the function f. So codomain we have, codomain is k. Codomain of the function is k. That means they are scalars. So on scalars we have the modulus norm, right? That means the norm is modulus, and that is again n for all n belongs to n. So this condition again fails because fxn is n. Again we are getting here n, and that is less than equals to alpha times norm xn, and norm xn is 1. So that means n is less than equals to alpha. That is not possible for every natural number n. Right. So therefore there does not exist alpha greater than 0 such that modulus of fx less than equals to alpha times norm x for all x in the domain. So domain is C101. Right. Again, alpha does not exist. That means f is not continuous. Not continuous means it is a discontinuous function. Yeah. So again, when we say f is discontinuous, we are not saying f is not continuous at what point. Right, because we are dealing with linear functions. So we have seen one result that f is a linear function and it is continuous if and only it is continuous at origin. Right, so therefore essentially f is not continuous. That means we are checking the continuity at origin. So it is not continuous means it is not continuous at origin. Okay, so this was the first example. Second example is another infinite dimensional vector space we have seen are the sequence spaces L1, L2, L infinity, and in which we have discussed one example C00. So the set of sequences which has only finitely many non-zero terms. Right. So let us consider a function f from c00 to k. So again, this is a functional, right? So defined by so we are defining this function as fx is equals to sum of all the coordinates of x. Right. So what is x here? X is basically element of C00. That means it is a sequence. Right. So x is a sequence whose only finitely many terms are non-zero, other terms are zero. And what f defines is we are adding all the coordinates of this sequence. So does this series converge? Yes. So if x is element of C00, then whether this series converges.
So you are asking this to yes, na? Gaurav.
Yeah.
Okay, okay.
So I hope we'll.
Yeah, yes, sir. I'm thinking about it.
Okay. Yeah, Jayesh.
Yes, sir. It should convert if we check that property, I guess.
Yeah, so x is element of C00. So what does this means?
Hmm. Set of all continuous and differentiable function at origin.
No, no, no. C00 means we are taking sequences. You see the element. X is x1, comma x2, comma xn. So that is a sequence. Sequence whose elements are either real number or complex number. And C00 means those are the convergent sequences which has only finitely many terms of the sequence which are non-zero. Other than finitely many terms, the other terms are zero terms. Right, so that is we will use here. So since x belongs to 0, 0, 0, only finitely many terms are non-zero. Other terms are zero. So when we add those terms, only this term will become finite sum because other terms of the series are zero. Right? So therefore, this series is always convergent because we are taking x from C00. If we take x from any sequence that this may not converge, for example, if we take x equals to 1, 1, 1, so on, is element of L infinity, but it does not belongs to C00 because this sequence has infinitely many terms which is non-zero, right? So it does not belongs to C00. And when we add this coordinate, it becomes 1 plus 1 plus 1, so on. So sum is infinite. So it is not a convergent sequence, right? So therefore, we are not taking elements from L infinity. We are taking elements from C00. So this series always convergent. Okay, so now we have defined this function. The question is that whether this function is linear. So that is very clear uh, because if we take two sequence, so x already we are taking from C00. Let us take y1, y2, another sequence from C00. Then f of y will be summation coordinates of y series. So that is summation yj j1 to infinity. Again, this is also we are writing j1 to infinity, but not all coordinates are 0. Only finitely many is non-zero. So therefore, what is x plus y? X plus y is the series coordinate-wise addition. So x1 plus y1, x2 plus y2, so on, right? And therefore, what will be f of x plus y? X plus f of x plus y is the sum of the coordinates of x plus y. Right? So coordinates of x plus y are these coordinates. So that is basically summation xj plus yj. And then since both of these series is convergent, this series is also convergent and this series is also convergent, we can separate this series. And then we know that this is nothing but fx, this is nothing but fy. So f preserves linearity. And similarly, f of alpha x is alpha fx. So it preserves the scalar multiplication. Yeah, so always I'm saying the second property is similar, but you should try to prove it. And it is not difficult. Here we are using the property that sum of this series is series of the point-wise addition is addition of the series. So that property we are using. The same property we can use here, that is when we multiply alpha with xj, and alpha is a fixed real or complex number, and when the series converges, we can take alpha outside. All these properties of series we already know from real analysis as well as mathematics 1. Okay, so f is linear. Now the next question is whether this function is continuous. So for continuity, again, what we need? We need to define the norm. So here we will take modulus norm. Here what norm we can define on C00? We recall we have defined a norm on C00 earlier. So C00 is a subset of L infinity, right? So we can define infinity norm on that. So now consider C00 as a norm linear space. It is also already a vector space. C00 is a vector space. Now we are considering norm on that. So the norm we are considering with respect to supremum norm. Right. So on C00 we are defining supremum norm, and on K we usually define the modulus norm. Right. There is no other norm which we define on real and complex number. So with respect to that, whether this function is continuous or not. So what we'll do if we want to show it is discontinuous, what we will do? What we need to show? Okay, Manavi, what condition we need to check for continuity?
Sir, there exists alpha such that the norm of fx is less than alpha norm of x. So if there does not exist any alpha, then f is not be continuous.
Not continuous. So basically we need to find yeah, so if you recall in the previous example when we have proved that the function is not continuous, we shown alpha does not exist by considering the elements of norm 1. So that means we need to find a sequence of elements of C00. So that is basically a sequence itself, and it has uh, yeah. So if basically let me write down the condition what actually we are using. So if we can find a sequence xn in C00. So sequence in C00 means each xn is element of C naught naught such that its norm is 1. Right, so all these are unit vectors. So this norm we are considering such that fxn is not bounded. So fxn is not bounded. Fxn is f is a linear functional, right? Because its codomain is complex number, real or complex number. So f is a linear functional. So let me mention it somewhere. So f is linear, therefore f is a linear functional. Functional means it is a linear function whose codomain is k. So such a maps are called functional. So whenever we have a functional and we want to show it has a sequence of unit vectors in the domain such that its image is unbounded. Is unbounded. If we can do this, then f is discontinuous. Right. So this is exactly this thing we have done in the previous example, but there this set was not C00, it was the continuously differentiable function on closed interval 0, 1. It was that set. But now here we need to find sequences whose supremum norm is 1. So what is the supremum norm of a sequence? So note that if we have a x which is sequence in C00, then the definition of sup norm is what? That is basically supremum of modulus of x1, modulus of x2, modulus of x3, and so on. Right. So each of the entry of the sequence we will take modulus, and then supremum is will take of these entries, and we want xn such that this supremum is 1. Right. So supremum is basically kind of maximum because C00 has only finitely many non-zero terms. So for C00, supremum norm is actually maximum norm. So maximum value of the modulus of each entry is 1. So in particular, if we take the sequences of the form whose coordinates are only 1 and 0 elements, right? So that is the simple elements which are the unit vectors. So yeah, so what are the unit elements here? So for example, 1, 1 by 2, 1 by 3, 0, 0, 2. So this has norm 1 because if you take modulus, it's even this has, if you take modulus, the entries are 0, 1 by 2, 1 by 3, and 1. The maximum is 1. So this is a unit vector. in C00 with respect to this norm. Right, so if you take x equals to this, supremum norm is 1. There are many other examples, but what we will consider in this example is we will consider a simple sequence of elements. So what we want the elements whose maximum value of the each entry is 1, such that f of xn is unbounded. What is f of xn? F of xn is the sum of the coordinates of the sequence. Right. So we want sequences whose elements are less than or equals to 1. Suppose we take all the elements are non-negative, then we don't need to take the modulus, right? If you can find the sequences whose elements are less than or equals to 1, so that some of the coordinates will increase. So can you give such examples, such sequences, so that its entries are less than or equals to 1, but some of the entry increases? So which sequences will take x1, x2, xn, x3, x4, so that the entry of the sequences are less than or equals to 1, but when we add the coordinates, it converges to infinity. So if you think, then you will come across very simple example. So let us, yeah,
Take 2 by 3 means every term has 2 by 3.
every terms 2 by 3 will not be element of C naught naught.
Okay. Yes, sir.
So we need terms. So for example, after some stage, all the entries are 0. So those sequences, so that each of the entries is less than equals to 1, but sum of the coordinates is infinity. Yeah, so I'm giving one example. Later on, you can find similar example also. It is not difficult, but it needs a thought. So let xn we are taking, that is the sequence is 1 1 1 1 and then 0 0 0. So first n entries are 1 and then other entries are 0. That is the sequence. So that means, so this we are defining for every n. What does this mean? This means x1 is 1 0 0, x2 is 1 1 0 0, and so on. So we can see that each of these norm of xn, subnorm of xn, is basically supremum of 1 1 1, right? First n entries. So supremum is basically 1, because we need to take modulus of each entry, but there are only 2 entries, 0 and 1. So both are positive. So modulus is also 0 and 1, and then its supremum is 1. So each xn has norm subnorm 1, and then what else we have? Yeah, so we need to check the f of xn. What is the norm of that? Right. So now norm of fxn. So what is fxn? Fxn is sum of the coordinates. So if you take xn is this sequence, sum of the coordinates will be what? Sum of of the coordinates of xn will be
N.
n, right? Because 1 plus 1 plus 1 n times, other entries are anyway 0. So yeah, so f of xn is n, and then its modulus is also n because n is a natural number. So modulus of fxn is n for every natural number n. Right, so now we can see that fxn modulus is natural number. So basically f of x1 is 1, f of x2 is 2, and so on. So this number is increasing. So it is unbounded. Basically what we are saying is as n tends to infinity, mod of fxn converges to infinity. Right, so therefore there does not exist alpha greater than 0 such that fxn is less than equals to alpha times norm xn. Right. In fact, we need to prove this for every x, but even it is not true for xn for the particular elements. So therefore f is not continuous. So in this inequality, why I am taking here modulus not norm? Why I am taking mod fx not norm fx? Because f is a functional. See, what is the definition of f? F is from C00 to k, and k has norm which is modulus, right? And C00 has norm which is supremum norm. So that is the reason why instead of taking norm fx less than equals to alpha times norm x, I have written modulus fx is less than equals to alpha times supremum of norm x. Right. So this you should remember when we are taking modulus, when we are taking norm. Right. So when we have a functional, we take modulus. When we have a non-linear space where the norm is other than modulus, we take norm there. Norm of the codomain. That will be norm of fx, because fx is element of codomain. Okay, so now I will give an exercise. Yeah, so let us discuss one more case. So this is example number. Okay, so in this example, what we have discussed is we consider this functional, which is a basically sum of the coordinates. That functional we consider, and then on C00 we consider the supremum norm. But C00 is also subset of other sequence spaces. Okay, so now let us take a remark, consider it as a remark. So in previous example, we can also consider C00 as a subspace of L1. Right, so what is L1? L1 is basically the set of all sequences from whose entries are either real or complex number, such that they are absolutely convergent. So absolutely convergent means modulus of xj is finite. Sum of the modulus of xj is finite. Right, because what are the element of C00? They are the sequences which has only non-zero, finitely many non-zero terms. So therefore, again, this is a finite sum because this sum has only finitely many xj which is non-zero. So this sum cannot be infinite. It will always be finite. So all the sequences in C00 are elements of L1. And then we know that on L1 we have the norm which is one norm and that is defined as this quantity. So that is summation j1 to infinity modulus of xj. Right. So that means since C00 is a subspace of L1, we can define the same norm on C00. So subset we cannot define, but on subspace we can define the norm, right? Because we need zero element for the properties of norm, and the other properties also we need scalar multiplication and addition. So therefore, we can assign one norm on C00, right? So now with respect to this norm, this linear function is whether it is continuous or not, right? So question is clear, right? So we are taking the same linear functional f, which is sum of the coordinates. It is a function from C00 to k, but here instead of defining supremum norm on C00, we are now defining one norm on C00, right? And on k we have anyway modulus norm. So with respect to these two norms, now the question is that whether this function is continuous or not. Right, so first thing is we need to find the elements. We need to try to find the elements from the unit circle, and then we need to see what is mode fxn, whether it is we can get mod fxn unbounded or not, right? So note that if so let us write down the criteria of continuity. So to check f is continuous, what we need to check, we need to find alpha greater than 0 such that modulus of f x is less than equals to alpha times norm of x. Right, so here norm x is not infinity norm because now we are defining one norm on C00, one norm on domain. That means this is one norm. So x is C00, x is element of C0 node. Right. So that means let us simplify this by, because we know what is our function and what is our one norm, right? So that is we need to find some alpha greater than 0 such that modulus of fxn. So what is fx? So if we take x equals to x1, x2, xn, then fxn is sum of the coordinates. It is our linear function. Right? Linear transformation we are taking, it is a sum of the coordinates. Whatever x we are taking, addition of that. So here we are not taking modulus. Note that here we are not taking modulus because this is a linear function. But here when we have defined the one norm, we have taken modulus. Because this is a norm. It should be non-negative number. Right? So by the definition of function, we need to find alpha greater than 0 so that fx. So what is fx? Fx is summation xj. j1 to infinity is less than equals to alpha times one norm of x. So that is this one. So that is modulus of xj, j1 to infinity, right? For all sequences x equals to x1, x2, xn, which is element of C0 right? So we need to find such a alpha. Now can you tell me what is the possibility of alpha? If you have any series, can we find some number such that modulus of the series is less than equals to alpha times the modulus value of the series? So what is the simple choice of alpha? So for example, if we have a series, actually we need convergent series. I'm just saying for any series, right? I'm not saying elements of C0. So do we have any inequality between, if you write in your known notation, then it is exactly, this is what we are saying is summation xn then what is the alpha?
Alpha is 1 actually.
1 or bigger than 1, right? Okay, at least for 1 it is satisfied. This is always true for every xn. For every convergent series, this is true. Right. So yeah, so that is what we are saying here. That in fact, for this norm 1, if we consider norm 1 with respect to this functional, then this is always true. For alpha is equals to 1, and therefore f is continuous. So basically this is absolute convergence that we are using here. Every absolutely convergent series is convergent. So that is exactly this what we are using here. Yeah, so this happens only if we take the one norm, because if we don't consider here on C001 norm, then here we will get different quantity. If we consider sup norm, then we'll get here supremum condition, right? In that case, therefore it is not continuous, but here it is continuous because we are considering one norm. So this is an example which is a linear function on C00, but with respect to two different norms, with respect to one norm it is continuous, with respect to other norm it is not continuous. Okay, so this is the example which we wanted to discuss. Now, next concept which we want to study is you can see similar examples in books. There are many examples considered related to linear and linear continuous and non-continuous examples with respect to different norms, so that you will be habitual with this finding alpha. So see some solved example and try some exercises. So next concept is homeomorphism. So do you remember what is homeomorphism? Have you studied?
Yes, sir.
So what is that? Homeomorphism means?
Sir, if it is a map f from x to y, then if fx f inverse is continuous, f is continuous, and f is a bijective map, then we can say that f is a homeomorphism.
Homeomorphism. Okay. So basically it should be invertible, so we can find its inverse, and then inverse is also continuous. Function is continuous, inverse is also continuous. And yeah, so but we know that every function is onto its image. So generally we don't need to assume the function is bijective. It is enough to assume the function is injective because it is always onto its range. Yeah, so homomorphism also we can consider for the function which are injective and the function and its inverse is continuous. So again here for continuity we need to assume the nonlinear species. So let x and y be nonlinear species. A function, a linear function f from x to y is called homeomorphism. From x onto range, right? So homeomorphism from x onto range if f is injective continuous function and f inverse, that is a map from range of f to x, is also continuous. So range of f is a subspace of y. So same norm we can consider on fx, range of f, and yeah. So I think we have discussed that if f is a linear function, then f inverse is from range to f, range of f to domain is also linear function. Right. So that is a simple result of linear algebra. So one result which we want to discuss is given function f from x to y linear map, then f is a homeomorphism. So basically it is from x onto the range if and only if there exist two positive numbers. So in continuity we take that norm of fx is less than or equals to alpha times norm x, but here there are two positive numbers exist, alpha and beta. So there exists alpha greater than 0 and beta greater than 0, such that we have, so the condition of continuity is this, right? So we already know if f is continuous, then it satisfies this condition, right? But now we have f inverse is also continuous, so that means this greater than equals to beta times norm x. So kind of squeezing is happening here. So let us prove this is very simple result. So let us prove the forward part. So we will assume that f is a homeomorphism and we will find alpha and beta. So one part we already know, what we discussed just now, that if f is continuous, then alpha exists. So if f is continuous, then we know that there exists alpha greater than 0 such that, so we know that means basically we are using this theorem, right? If f is continuous, then there exists alpha greater than 0 such that norm of fx is less than or equals to alpha times norm x for every x in the domain. Now, to find the other beta, we will need to consider what we know is, if hypothesis we have f is homeomorphism. So again, we can use another alpha exists, that is beta, for the inverse function. Also, f inverse, which is a map from range of f to range of f to x, is continuous, right? Because f is a homeomorphism, so its inverse map is also continuous from fx to x. Fx is the range of f, and therefore there exists another positive number. So therefore there exists alpha greater than 0 such that norm of, instead of fx, now we have f inverse of the element, right? So f inverse of some element y in the domain. Domain is range actually in this case. F inverse of y, f inverse of y is less than or equals to beta times norm y for all y in the range, right? Y in the range of f. The same condition we have written for the f inverse function. Okay, so now if we substitute, we know that y is in the range of f. Therefore, y is equals to f of, let us take y is equals to fx, right? So fx, the same x, we are taking f of x is element of y. So therefore, for y is equals to f of x in range of f, we have, so we substitute y equals to fx, then we get f inverse of fx, that is norm of x, which is less than equals to beta times norm of y. What is y? Y is f of x. Right. So, okay, so we need to write here beta, but now again we need to convert it into beta. So let us consider this another number, gamma. Right. So like here alpha exists, here gamma exists, which satisfies this property, and therefore by substituting y equals to fx, we got this equation. And why I have taken gamma? Because we need constant on this side, right? So therefore we'll multiply by gamma inverse. So therefore gamma inverse norm x is less than equals to norm fx for all x in x. So now this is our beta. So take beta is equals to gamma inverse. Now we got beta times norm x is less than equals to norm of fx. That is this condition, this part. Right, so alpha exists because f is continuous, gamma exists because f inverse is continuous, and then gamma inverse satisfies this property of beta. So one part we have done. Now the converse part. So you can see that here that everywhere we are using linear algebra as well as properties of non-linear species, basically the continuity. So what is the converse? Converse is that given that there exists alpha greater than 0 and beta greater than 0, such that just 1 minute. हाँ, तो ये alpha beta exists, that is given. Alpha, there exists alpha greater than 0 and beta greater than 0, such that beta times norm x less than equals to norm fx less than equals to alpha times norm x for all x in x. So that is given, and what we need to show is we need to prove that f is a homeomorphism. हाँ, तो ये अब इसका क्या करेंगे? So what is trivial? F is continuous is easy, or F inverse is continuous is easy from the hypothesis.
By previous definition, f is continuous is already we have.
Yeah, so this condition we can use since alpha exists, f is continuous, this part. So 5 implies 3. Yeah, so since norm of fx is less than equals to alpha times norm x for all x in x. So since there exists alpha greater than 0 such that this happens, we have f is continuous. Okay, so every time whenever such condition is satisfied, that doesn't imply f is continuous. It will imply only when f is linear function. Right, so this condition is very important, right? So keep it in mind that whenever such condition is satisfied, we need linearity of the function. So one part it is clear, f is continuous. Now the second part is f inverse. Anyway, we can define from the range of f to f, and yeah, but the first condition is f should be injective. right? And again by the same condition, so to show that any linear function is injective, we need to just check that kernel is 0, right? So since f of x is equals to 0 implies x equals to 0, f is injective. Right. So what we are using here is we are using norm of fx is less than equals to alpha times norm x. So whenever fx is 0, so we are using the other part, beta part actually. So beta times norm x is less than equals to norm of fx. Right. So whenever fx is 0, norm of fx is 0, right? And then if norm of fx is 0, this part is 0 and beta is positive. So that means norm of x is 0. Norm of x is 0. That means x is a 0 vector. Right. So this is true for every x in x. So using this part, so such a condition, this condition is known as bounded below. Right. So that alpha condition is known as bounded above. Right. F is bounded above because norm fx less than equals to alpha times norm x. Here we are getting bounded below because beta is coming on the left side. Whenever the function is bounded below, it is always injective if it is a linear function. And the last condition is that f inverse is continuous. So again, in the continuity part, this beta condition will be useful. So since beta norm x is less than equals to norm of fx, whenever we have, so to check f inverse, which is a map from range of f to x, right? To check this is continuous, what we need a sequence in range. So that means whenever fxn, which is a sequence in range, it converges to fx, we need to show that f inverse of the sequence converges to f inverse of fx, right? So that is what f inverse of fx is xn and f inverse of fx is x, right? So this is xn, this is x. So this is our claim. So if we are given these, if we can show this, then inverse is continuous. And that is obvious because of this. Right? Because whenever fxn converges to fx, xn will always converge to x because f is a linear function. Right? So let's call it star. So from star norm of, so what is fxn minus fx? That is basically norm of fxn minus x because f is continuous function. Right, so this is what this is greater than equals to beta times norm of xn minus x. This is the reason why this condition is satisfied, and that is essentially the proof that f inverse is continuous. So we have verified the continuity condition for f inverse in terms of sequences. Okay, so this is enough for today. So let me stop the recording. If you have doubt, you can ask.